Hey everyone, in this video lesson, we're going to continue talking about geometric vectors in a new sense. We're going to talk about the geometric dot product. So let's get started. The application or motivation we're going to use to start is a physics application. Many of you guys who are taking this course have taken physics, and in grade 11, you learned about work and how to calculate work. Well, work is connected to our dot product. So just as a little review of work, mechanical work is the product of the displacement traveled by an object and the force applied in that direction of motion. And if you took physics, you learned that the units of work are the Newton meter, which is equivalent to joules, the unit for energy, because work is just essentially a change in energy. If you apply a force onto an object and it moves, we say you've done work on the object. And the way we calculate work is some kind of multiplication between the force vector and the displacement vector, but those are not numbers, they're vectors, and the force doesn't always work in the direction that the object moves. For example, if you look at this person pulling a sleigh, they're pulling at an angle to the ground. The sled moves. That is an awful parallel line. It's because I'm writing with my mouse right now. I should write with my tablet, but that's a delta D, by the way. But the sled is moving up the hill, and there's an angle theta between them. And so this idea of work involves a product, which we're going to define, of these two vectors in a second. Let's actually do an example with work. Consider Max pulling a sled up the hill there. You've got him applying pulling along his rope, applying a force at an angle of 20 degrees to the slope. But the displacement, we'll call it S, is actually going up the slope. And so in your grade 11 physics course, you might have calculated the work this way. And maybe you used slightly different variables or notation, but the idea is the same. So the work is the size of the force times the magnitude of the displacement times the angle of the angle between the force and displacement. So why the cos theta? Well, because if the force isn't acting in the direction of the displacement, and work is defined as the magnitude of force, or the product of displacement times magnitude of force applied in the direction of motion. So if you want to turn that force into a component in the direction of motion, you've got to break it into a component, and using trigonometry, this would be the adjacent side. The length of this side would be F times the cosine of 20. And so you get F cos 20 magnitude times the magnitude of S, and that's where this comes from. And we can actually, now that we have those things, we can just calculate the work. So that's 120 times 100 times the cosine of 20. And the answer is almost like not too important here, just the connection between vectors and work right now. But let's just finish it off. About 11,300 joules, Newton meters of work, or joules, whatever you prefer. What we're going to see in a second is that work is, the formula for work is F S cos theta, but this is actually defined as the force vector dotted, a dot product between the force vector and the displacement vector. So when you guys were in your grade 11 course doing Fs cos theta, you're actually applying the dot product. It was the dot product between the force vector and the displacement vector. In previous lessons, we've talked about scalar multiplication of vectors. Today we're going to talk about one of two products. Today we're talking about the dot product. In a future lesson, we'll talk about the cross product. And today we're breaking our dot product lesson into two parts. Today we're focusing just on what we call the geometric dot product. So we're just going to look at geometric vectors today. We won't worry about the Cartesian plane. So the dot product between two vectors, if an angle between them, is defined as the following. So here you have two vectors A and B and the angle between them. And remember, angles between two vectors are always tail to tail. So that's really important. I'd even write that down as a little reminder for yourself. When you're finding the dot product between two vectors, you need to know the angle between them, tail to tail. It's defined this way. There's my cursor. If I want to take two vectors and find the dot product of them, and so sometimes you just say A dot B or A dotted with B, we take the magnitude of A, we multiply by the magnitude of B, and we multiply by the angle between them. This is the dot product of two vectors. You sometimes will see the dot product referred to as the scalar product of two vectors because the result here is a scalar, right? Magnitude of A is a scalar, magnitude of B is a scalar, cosine of an angle is a scalar, and so this is a scalar. So you get, when you dot two vectors together, you get a scalar. That's important. Couple notes. What happens if A or B equals the zero vector? Oh, that shouldn't be a theta. That should just be a zero. Got too fancy there. Yeah, what happens if one of them is the zero vector? Because that's kind of weird. Because how do you find the angle between the zero vector and a non-zero vector? Well, we're kind of saved thinking about that because if the zero vector, the magnitude is zero. And so you get zero times anything, and the dot product would be zero. Dotted with B equals zero. And the second little note there, so for work, when you dotted a force and a displacement, the units were Newton meters or joules. I'll just say the units depend on the application. If you're just taking two generic vectors, we don't have any units there. But if you're applying it to some physical problem, you've seen that the dot product can be applied to work and the units are joules, but the dot product can be applied into a lot of other examples in physics where the units would be different. Let's continue. So let's just get used to this idea. Let's say I have two vectors, U and V. Angle between them is 75 degrees. So something like this. Remember, the angle between them is tail to tail. We have U being smaller than V. I mean, something like that. The diagram is not too important here. U dot V, we take the size of U, we multiply by the size or magnitude of V times the cosine of the angle between them. So here that's 5 times 8 times the cosine of 75, which we can just do very quickly. And we get about 10.4. So you may be wondering, what does this 10.4 signify about the two vectors? Does it have any special meaning? And the answer is not really. When you take the dot product and apply it to some context, it has some meaning. But this 10.4, there's two generic values, doesn't really have any specific meaning. We'll talk about how the sign can be relevant. But yeah, this 10.4 doesn't really have any significance. It's not some property of these vectors. So there's our first dot product example. Pretty simple if you have the magnitude and angle between them. Second cool thing is that you can actually, if you know the dot product between two vectors, you can actually find the angle between them, which actually makes sense, right? So U dotted V is the size of U times the size of V times the cosine of the angle between them. Well, that would imply that if you rearrange things, the cosine of the angle is the dot product divided by the product of the magnitudes. So we can do that for our example here. The dot product is 0.6. U and V are both unit vectors, so we know that that means they're magnitude of 1. Take the inverse cosine of 0.6. Make sure you're in degree mode. I think I am. Yeah. About 53 degrees is the angle between these two vectors. This will be really helpful and useful once we talk about algebraic vectors. And you're going to see, much like adding and subtracting vectors was super easy once we used a coordinate system. The dot product is too, and you can do some super powerful stuff, easily finding the angle between two vectors. But we got to start somewhere. So if you know the dot product, the two magnitudes, you can find the angle. I guess if you knew any three of these four, you could find the fourth thing. Let's go on. Right. Something cool about the dot product is it gives you a method to determine whether two vectors are perpendicular, right? Because if u dotted v is size of u times size of v times cosine theta, well, if we think about, we know about, we've been studying trig for a long time. If the angles between 0 and 90, then cosine is positive, right? It's in terms of the cast rule, we're in this quadrant here, 0 to 90, cosine is positive. And so if the angle between the two vectors is acute, from 0 to 90, then the dot product will be bigger than 0 because cosine theta is bigger than 0. And of course, magnitudes are always positive, right? Here's the cool thing: for if theta is 90 degrees, well, we know the cosine of 90 degrees is equal to 0. So it doesn't matter what the size of the vectors are. If you have two vectors that are perpendicular, the angle is 90, the dot product up between them will be 0. So that's pretty cool. And if the angle is between 90 and 180, I should actually have a square bracket here because you can have an angle between two vectors being 180. Cos theta is negative, so the dot product will be negative. So that actual number you get when you do the dot product does have some meaning in terms of the sign. If the angle between them is positive, then the two vectors are kind of pointing off in the same direction. If the cosine, or if the angle is 90, then they're obviously perpendicular. And if the dot product is negative, you know that the two angles are kind of like, working kind of against each other. That's very loosely speaking, but it maybe helps you a little bit, give you some meaning to the dot product. And again, a little note here: two non-zero vectors, non-zero is the important word there, are perpendicular if and only if A dotted with B equals 0. So if you know the dot product is 0, automatically the vectors are perpendicular, as long as they're non-zero vectors. Because if you just have two vectors, A dotted B is 0, one of them or both could be the 0 vector. But if they're not, you know they're perpendicular. So that can be very useful. The dot product obeys some properties. So much like the product of two numbers obeys a bunch of properties, so does the dot product. The dot product obeys a commutative property. That means that the order doesn't matter. Whoops, that should just be equals B dotted with A. Excuse me. Because if you think about it, I'll just point to this. Like, u dot v is size of u, size of v, cos theta. Well, if I change the order, I'll have v first, then u. And that doesn't matter because we're just multiplying two magnitudes. And the angle between them doesn't change. The second property, it might be a little less intuitive, but it holds true. Excuse me, that should be a vector. So the dot product obeys a distributive property. So if I had something like this, A dotted with a sum of two vectors, B plus C. So those are two vectors. A is a vector, B plus C is a vector. We can do the dot product between them. This result is the same as if you did A dotted with B plus A dotted with C. It obeys this distributive property. The dot product of a vector in itself is pretty cool. So consider A dotted with A. What does that mean using the definition? That would be the size of A times the size of A again. And the angle between a vector and itself that's really, I'm just trying to emphasize that the angle between those two vectors is 0. If they're pointing right, if two vectors point in the same direction, the angle between them is 0. So the angle between A and itself is 0 degrees, and the cosine of 0 is 1. And that gives you this cool property that the magnitude of, or the dot product between any vector and itself is its magnitude squared. So that's pretty cool. And then we have an associative property. So what this means, say we have some scalar times vector A dotted with vector B. So right now, the scalar is associated with vector A. But the following would be equivalent. That same scalar, if I associated it with vector B, I get the same result. And if I actually just associated it with the dot product of A and B, those are all the same. That's the associative property, is that a scalar can kind of move kind of wherever it likes in that operation there. So those are the 4 properties we may make use of. Let's just do an example, getting used to some of these properties. Let's look at this first one. So we've got the dot product between a vector multiplied by a scalar and the sum of 2 vectors. So we can definitely use the distributive property here. So this would give us KU dotted with U plus KU dotted with V. And then, so that's the distributive property. And then we could write that as K times the size of U squared plus K times U dotted with V. And that would be kind of as far as we could go. Depending on the application, like maybe you could play around with this a bit more. So for example, I could write, I'm not saying this is what you have to do for this one, but we could write U dot V as UV cos theta. And then I could factor out a K and a magnitude of U. And what I'd be left with is U plus V cos theta. So I think this is the intention here, but I'm just trying to point out that that should be magnitudes too. Magnitude. Depending on the application, like any of these properties can help out. The next one's pretty cool. If you take the sum of 2 vectors and dot it with the difference of those 2 vectors. So we use the distributive law. And we know from algebra in grade 10 that the doubly distributive law applies like so. Use FOIL. So what do we have? We'll have R dotted with R minus R dotted with S. So that's like R dotted with negative S, right? We know that the associative property says you can pull out that negative. And then we have S dotted with R. And then we have minus S dotted with S. And so we've used various properties there, but it's just basically FOIL. R dotted with R is the size of R squared. Check this out. R dot S and S dot R are the same via the commutative property. And then we're adding and subtracting. Those actually go away to 0, right? Those cancel out. And then we have minus S dotted with S would be the size of S squared. So that's pretty cool. And I suppose, I'm not saying, I think this is what the final result we're looking for, but depending on the application, like you could factor that too, right? That's a difference of squares. So that could be the size of R plus the size of S times the size of R minus the size of S, which is pretty cool that you have that kind of parallel between the vectors and dot product and their magnitudes and just the distributive law. All right, so that's it for today, actually. We're going to save the algebraic dot product and apply the dot product to a Cartesian plane for our next lesson. For today, you should just be super comfortable with the definition of the dot product, playing around with that, finding angles, knowing how to find angles or if 2 vectors are perpendicular via this property. So it's actually a pretty light day. I have some practice for you guys. It's actually pretty light. because you're just focusing on the geometric vectors part of this section. In our next lesson, at algebraic vectors, and we'll draw more practice from that. That's it for today, guys. Hope you're staying well, and we'll see you guys soon.